Okay, Unit 6 today, which is the last unit before the next exam, right? Which will be on Wednesday. This is acid-base theory. And there are different types of acid-base theory depending on which area of chemistry you're looking at. For example, in OChem, organic chem, you're generally looking at Lewis acids and bases. Biochem and most areas of general chem favor Bronsted-Lowry. And then we have Arrhenius, which is, to a certain extent, just historically important. Okay, but we're going to look at the Arrhenius definition and the Bronsted-Lowry. It's going to go a little bit out of sequence with how it's presented in the book. All the topics will be covered, but I don't cover them quite the same way that they are in the book because I think the continuity is interrupted a little bit. I talk about Arrhenius, then go right into Bronsted-Lowry, not do Arrhenius, then calculate pH and do other things, and then come back and start talking about acid-base theory. So it's all in there. Just understand that you might have to jump back and forth a little bit. Okay, under the Arrhenius theory, an acid is anything that produces H plus in solution. An acid is anything that donates or produces H plus in solution. And it's worth noting here that H plus is nothing more than a proton, right? If we have H plus, we look at the hydrogen atom. This is a hydrogen atom, right? Which actually doesn't exist in nature, right? It actually exists as H2, the diatomic molecule. We can make it though. Make it real easy. If you go H plus, that means that you have one less electron than the number of electrons required to be neutral, which in this case, since there's only one proton, is itself one electron. So if you get rid of the one electron on hydrogen to create H plus, you have nothing more than a proton. And the reason why I tell you this is because the terms are synonymous. So if you run into them in the lab or other textbooks, H plus and proton are the same thing. And in reality, doesn't exist in an aqueous environment, or these free H pluses. If you took an acid and you evaporated all the water off the acid, you would not have a beaker full of protons. Okay? The protons actually exist only as free protons, only in the gas phase. In the laboratory, it actually exists as a protonated water molecule called hydronium ion. Called hydronium. This is what we really see in the lab. And when we're talking about acids and bases and protons and things like that, these are terms that we use as a matter of convenience. In reality, this is how it exists. It's H3O plus hydronium. Okay. Notice, this onium. We saw it, and ammonium. Remember, NH4 plus was ammonium. Whenever you have a reasonably electronegative element, like nitrogen, oxygen, carrying a positive charge, it takes this onium ending. Just a little aside. Okay, so I usually refer to them as protons. Okay, so an acid is a proton donor to solution. Anything that produces protons, H pluses. This is Arrhenius, right? A base is anything that produces OH minus. Okay, so these, like I said, these still have historical importance, and we still use them when we start calculating pHs and pOHs. Under the Arrhenius theory, acids produce H+, bases produce OH-. Okay, cut and dry. But then you run into things like ammonia, NH3. This is a base. This is a base. And you're saying, what the heck? Under the Arrhenius definition, it's got to produce OH, and ammonia doesn't have any oxygens in it. So there were compounds that existed that were in apparent contradiction to the definitions presented in the Arrhenius theory. In reality, it wasn't. It's still a base. I can show you in just a minute. But there were some things that were cause for confusion. It turns out that ammonia does not ionize. Remember we talked about ionizing, produces ions in solution. Ammonia doesn't ionize unless you add water to it and make it aqueous. Once you add water to it, you get the following. You get ammonium hydroxide, which quickly dissociates and ionizes into ammonium plus hydroxide. So there it is. Okay? But again, this will only occur if you have water in your ammonia solution. And everybody smelled ammonia. This is a cleaning solution that we use, routinely clean floors and stuff. It's also one of the things in smelling salts. Wake you up when you get knocked out. Okay, so there were things that didn't, at least on the surface, agree with Arrhenius. So two other guys by the name of Bronsted and Lowry. Some people just call this the Bronsted theory, but I'm going to give credit to Lowry. This is the Bronsted-Lowry, and Bronsted is German, I believe, I hope. Bronsted-Lowry definition, acid is the same. When you look at the Bronsted-Lowry definition, the acid is exactly the same. Anything that produces a proton or donates proton to solution produces H+. The base is somewhat different. Bronsted-Lowry describes as base, or a base under the Bronsted-Lowry definition, is an H+ acceptor. Anything that accepts H+ is a base under the Bronsted theory. Now, one consequence of Bronsted-Lowry was you couldn't have one without the other. You can't have one without the other. If you have a proton donor in solution, you must have a proton acceptor. In fact, it's actually the acceptor that defines the donor. Okay? A proton donor does not become a donor until something in solution actually accepts the proton. Okay? It's very similar to a donation you make, a charitable organization. I write a $5,000 check, I'm going to stick it under the tire of the car in your garage that hasn't moved for 3 years, and then you go do your taxes and you say, no, I gave a $5,000 donation to the United Dog Fund or something. And they say, great, that's a write-off. Let me see the canceled check. Well, you don't have that. You don't have that check. it doesn't become a donation until someone accepts it. Same thing here. Okay? They define each other. So, something very interesting results from that particular requirement in Bronsted-Lowry. So let's see if we have some. I can make them up, but I don't like flinging when the camera's going because this stuff sometimes doesn't work. Now, the one thing that will always be true, okay, when you see this, it's always an acid, always, no exceptions. This is always acid, and this is always base. This will always be true. Can't make too many of those statements in chemistry that have the words like always and never in them. When you see H3O plus, it is acid. When you see OH minus, it is base. The problem is that you don't always see them. There are examples of reactions that don't contain H3O or OH minus. But when you do see them, you can automatically label. We can do the one we just had up here, the ammonia. So let's take a look at an example. I'm going to put this aquated plus water goes to, I'm going to break this apart. Okay? Write this again. So I have this reaction, and you're not expected to come up with these, all right? This would be more along the lines where you'd say, well, here's a chemical reaction. And what I want you to do is label every species, every compound, neutral, or ion, as either an acid or a base. Now, this isn't as difficult as it might seem, because if you know one, you can get the other three, according to the Bronsted definition, Bronsted-Lowry. So, I'm looking at this equation. Is there anything that I know 100% for sure? What?
Water and the OH negative.
What about it?
OH negative is a base.
Right here it is. I know for sure that OH is a base, so I label it base. OH is a base. Bronsted-Lowry says you cannot have one without the other. So the other one must be acid. It's got to be. You can't have one without the other. Acid. See the nitrogen-containing compound? It differentiates itself from the oxygen-containing ion. These are both ions in the compound. If the nitrogen-containing species was an acid on this side, it's the opposite on the other side. Makes this a base. Bronsted-Lowry says I can't have one without the other. This must be an acid. Does everybody see that? It starts with identifying only a single species. Once you get that one under your belt, you can determine what all the other ones are. Everybody good? Now, the acid on one side of the arrow, reactant, and the base on the other side have a very special relationship. Acid on one side, base on the other, acid on one side, base on the other. Don't go acid-acid. It's not acid-acid. It's acid-base, acid-base. Everybody see that? These are called conjugate acid-base pairs. Called conjugate acid-base pairs. What's the difference between acid-base on one side, acid-base on the other side? What do they differ by? You got NH3 on one side, NH4 plus on the other. You got OH minus on one side and H2O on the other. H2O you could think about as being this, right? HOH. We'll see that next lecture. Okay.
So they differ by one hydrogen plus.
One H plus, right? Conjugate acid-base pairs differ by the proton, the H plus that is transferred. Let's see if our definition, according to Bronsted-Lowry, makes sense. NH3 is a base, which means it is an H plus acceptor. H2O in this case is an acid, which means it's an H plus donor. H2O donates H plus to NH3. NH3 was neutral, and it just took on an H plus, which means its overall net charge now has to be plus 1. And its hydrogens went up by 1 count. Makes sense, right? This donated acid, this accepted base. Make sense? Let's see if it works the other way. This is a base, this is an acid. NH4 plus, defined as an acid, has to donate H plus. If it donates H plus, its hydrogen count goes down by 1, and because it was positively charged and gave up the positive, it goes to neutral. The OH minus accepted the H plus, its hydrogen count went up 1, and the plus and minus cancel out and went neutral. So they do. Makes sense going both ways, right? Makes perfect sense going both ways. Now, incidentally, an acid defined under Bronsted-Lowry would be an acid under Arrhenius, which would be an acid under Lewis. Okay? These different theories just give you a different reference point for looking at how things are defined as, in terms of, what is an acid, what is a base. But an acid under one would be an acid under all of them. There's no conflict there. Okay? Let's do some other examples. This concept of conjugate acid-base pairs, it's important, and it's going to be important even in this lecture. Okay? It's going to be important when we get to buffers. It's going to be important when I ask you, what is the conjugate acid of this? What is the conjugate base of this? So let's take a look at another one. H2O is liquid. Yeah, pure liquid. What do we know for sure?
The OH negative.
The OH negative is a base. Bronsted-Lowry says can't have one without the other. If that is a base, this must be an acid. The dihydrogen phosphate ion. I look for something similar to the phosphate group. On the other side, there it is. If this was an acid, it makes it a base over here. Bronsted-Lowry says you can't have one without the other. That must be acid. Identify the conjugate acid-base pairs. I think the last example was the same way, right? Number 1 was with number 3 and number 2 was with 4. But that was just a coincidence. It's not always the first one here is going to be connected to the first one on the product side. And last one. Does everyone understand that? Yes? What is the conjugate acid of HCO3 minus?
H2CO3.
How do you know that?
Because it's, well, that's a base, so you're looking for an acid, so the acid needs to donate one, so a hydrogen, so you have to add another hydrogen. And then
That's exactly how I would have explained it too. Exactly. Maybe not word for word, but that's exactly. If you're being asked for the conjugate acid, what do you have? What were you given? The base, right? The base. That makes sense. They're not going to ask you for the conjugate acid and then give you the acid, right? So if you're being asked for the conjugate acid, you're given the base. What do bases do? So you have to increase this by H plus. Adding H will do that. Adding plus will cancel the plus and minus. Right? Everybody see that? First of all, you know, I mean, you're going to see these on the exam. 100%. Guaranteed. On the quizzes, on the exam. When you have this, and you're asked, what's a conjugate acid or conjugate base? You know that you only have two possibilities. There's only two possible answers here. This without an H plus, or this with an H plus. So scratch out the other two, because they're not even possibilities, right? The only two possibilities are taking H plus away from this, or adding H plus to that. Those are the only two possibilities. So you can narrow it down, just like that, to 50-50. Two answers, right? If you're asked for the acid, you're given the base. What do bases do except you're going to increase? Some students in the past have said, well, I think it's easier if you're asked for the conjugate acid to add. add H plus. What is the conjugate base of HSO4 minus?
SO4
Everybody get that? No? Get it, Matt? You got it? If you're asked for the conjugate base, you must be given the acid. What do acids do? They donate H plus. They produce H plus in solution. So you're going to lose H plus, which means this hydrogen is gone. And since you're subtracting H plus, it goes back down to negative 2. Okay? You will be asked to do that. You'll be asked 100% to do that. Always remember, conjugate acid-base pairs only differ by H plus. They only differ by H plus. If you see conjugate acid-base pairs, which we will see in a little bit, these are conjugate acid-base pairs because they differ only by H plus. It's real easy to figure out which one's the acid and which one's the base. Right? The one with a greater number of hydrogens. They're only going to differ by 1 H plus. The one with a greater number is the acid, the lesser number is the base. Okay? You're all experts now in the application of Bronsted-Lowry. Alright? A consequence, again, of Bronsted-Lowry is conjugate acid-base pairs. Okay? Because of the requirement that you have to have protons, donors, and acceptors in solution at the same time. Good. Now, there are varying strengths to different types of acids. Okay? Strong acids strong acids ionize nearly 100%. They ionize completely. Okay? HCl is a strong acid. In aqueous environment, in water, okay, there's a couple of different ways you can write this, but it's the same thing. Or you could also see it simply as removing the water because everybody knows it's there. that's aqueous. Again, I cannot put a Q. I can't write in cursive anyway. But trying to put a Q after an A just doesn't happen. These are the same things. What's more complete, what's more accurate? This one. Because it shows the water. It shows the conjugate acid-base pairs, right? In this case, HCl's acid, base, acid, base. But we could have worked backwards, right? We could have said this is acid right here, because anytime we see H3O plus, it's an acid. And besides, Cl minus has to be a base, right? Why? Why does Cl minus have to be a base?
The other one's acid.
It's what?
It's acid.
Because it's conjugate pair, isn't it?
Well, even more than that. Let's look at it even more on simpler terms. What do acids do? Donate what? H plus. Why does Cl minus have to be a base? It doesn't have an H plus, does it? See how there's no H plus there? So it couldn't donate. It's base. Acid. Base. Notice with the shorthand version, which is done as routinely, as a matter of convenience. Okay? It's a matter of convenience. It's done all the time that it's written this way. You can't identify conjugate acid-base pairs when it's this way, right? Can't do it. But HCl is a strong acid. And you know how I know it's a strong acid? It's on the list of strong acids in your book. That's the only way you know if something is a strong acid. You memorize that list. How many are on there? 6, 8? Depends on which book you look at. Usually there's 6. Right? Yep. We have 6. Memorize it. It'll be in your best interest to memorize it. Strong acids ionize completely. That's what should always stick in your mind when you hear the word strong acid. Strong acids break apart virtually 100% of the time. That means if you have HCl, hydrochloric acid, we'll get to the naming in just a minute. If you have HCl in water, aquated, HCl doesn't actually exist. The molecular form of HCl doesn't exist. Because every single one of the HCl's is broken apart into H plus and Cl minus. All it is a bunch of H pluses and Cl minuses floating around. Okay? Now, whether or not a particular substance will be a strong acid or a weak, we'll talk about weak in just a minute, is all related to how well the resulting negative charge is stabilized on the anion. Now, when you lose H+, I don't care where you're starting from, you're going more negative. If you're at -3 and you lose H+, you're going to -4. If you're neutral and you lose H+, you're going to -1. If you're +1 and you lose H+, you're going to 0. So you're going more negative. How well the resulting anion is stabilized will determine whether or not that thing even loses the H+. So you look at chlorine, very electronegative element, right under fluorine. All the halogens, group 7s, are very electronegative. Okay? Chlorine can handle a negative charge real well. So when it loses, HCl loses H+, the resulting anion is very stable. Okay? Strong acids ionize 100%, or virtually 100%. And strong acids are identified because you memorize the list of strong acids. Because anything else that is an acid that is not on that list is a weak acid. So do you want to memorize hundreds and hundreds of weak acids? Or do you just want to memorize 6 strong and say, anything else that's an acid is a weak acid? Now, what do weak acids do? What's the first big difference you see between those two equations? And again, you could also write this as okay, so we'll separate them right here. We'll put a line across here. Separate. HCl is a strong acid. I know that because I memorized my list of strong acids. I'm going to be rewarded probably tomorrow on the quiz if I memorize my list of strong acids. Wink, wink. Right? But when I look at these two, what jumps out at you?
Equilibrium arrows.
Yeah, perfect. The equilibrium arrows here. Right? It appears that the weak acids have reversible reactions and are in equilibrium, while the strong acids don't. And that's true. H plus will not recombine with Cl minus and form molecular HCl. Because we know that molecular HCl in water dissociates almost 100% of the time. Basically, they hate each other. And as soon as you give them water, a vehicle for them to ride apart from each other, they do it. They do it. And I think one of the more concentrated forms of HCl is 17 molar. It's very concentrated. Burn you quick. Down here, we have an equilibrium. Weak acids only partially ionize. They only partially ionize. That means weak acids exist primarily as a molecule in their molecular form. Very few of them break apart and form ions in solution. Some of them do, but they only partially ionize. That's the big difference between the strong acids and the weak acids. Okay? Is everybody good? Strong acids break apart virtually 100% of the time. Weak acids don't. That's what you remember. It will serve you well just to remember that. Okay? This is a dead giveaway, though. Equilibrium. Does everybody understand that, equilibrium? You sure? Okay. I'm going to give you an example that I think is really going to clear it up for you. You got all that?
How do we know if it's going to want equilibrium? Like if we're given just that first side of the formula, how do we know that it's going to be back and forth?
Because you're going to know that's a weak acid because it's not on your list of strong acids. That's it. That's all. That's all you know.
So anything that's not on the strong list is going to find equilibrium.
Acids, yes.
Right.
Let me give you this example as equilibrium, because I think it'll really clarify it. Clarify it a lot more than it is right now.
But not all weak acids find equilibrium.
Yeah, they do.
They always.
Yep. Yep. They do, because all weak acids have what we call a Ka value, which is an equilibrium constant. So yeah, let's take a look at this. This is just a little aside to help you understand more what equilibrium means. Let's say that I have two tanks, two water tanks, right? And my two water tanks are connected at 2 points. And they have pumps. Pumps only pump in one direction. Let me try and get this somewhat. So, I have two water tanks, and they're connected in at 2 points. And each of the pipes that connect them have pumps in them, but the pumps are one-way pumps. They can only pump one way. Right? And let's say I fill this thing up. Say I put, better not make that too high because I'm going to add some more water to it. Say I have 100 gallons in here. Just for the sake of argument. And I turn both pumps on. Both pumps. Nothing's happening here with this pump because there's nothing in this tank. This tank is empty. And I start pumping water between the tanks using this pump. This is analogous to the initial stages of a reversible reaction. In the initial stages, only the more favorable reaction is going to be running. Right? Because you have to generate enough product in order to initiate the reverse reaction. So, we're going to start pumping our water. So, here's our water, right? And what's going to happen over here is this is going to start to fill up. Our forward reaction. Are more favorable. Put this in here so you can see which way they're going. This fills up and only one of the reactions is proceeding until you hit a threshold value where you initiate the reverse reaction. And water begins to be pumped back into tank number 1. But it's still not being pumped in at the same rate that it's being pumped out. Diameter and length of these pipes are the same. Pumping power of the pumps are the same. Okay? So a little bit of the reverse reaction has started. Because you have to generate a threshold amount of product. The minute you form product, it doesn't just immediately reverse and go back. Otherwise, you'd never see any product form, right? None of it would ever be there. Because as soon as it formed, it would immediately revert back to the reactants through the reverse pathway. So, you have to have a threshold amount of products before the reverse reaction will initiate. And this thing will keep going. Once you hit a certain product or amount of products, your rate of reverse is equal to your rate of forward, and you have achieved equilibrium. Remember, equilibrium is about rate, not amounts. Does the amount of water in each tank have to be equal? No, it doesn't have to be. Can it be? Yeah, it can be, but it doesn't have to be. All right? Let's say, for the sake of an argument, we started out with 150 gallons here. And we end up with 50 gallons here. Right? That means we pump 50 gallons out. So this is now at equilibrium 100. The amount of reactants and amount of product at equilibrium do not have to be equal. Equilibrium has nothing to do with amounts. It has everything to do with rates. This looks like steady state. If you were up here in a chair looking down, you'd say, oh, that tank's not moving, and that tank's not moving. I'm at equilibrium. It looks like it's a steady state. But in reality, if you threw a piece of paper in there, you'd see the paper get sucked through, come back up, get sucked through the other. It's dynamic. There's a process going on. This is moving. It's in equilibrium. It just so happens that the rate of water being pumped out of one tank is exactly the same as the rate of water being pumped into the tank. So it looks like nothing's happening. This is equilibrium. Okay? The amounts do not have to be equal. They can be, but they don't have to be. That's not a requirement for equilibrium. What is interesting is that since it looks like steady state and nothing's going on, the ratio of the amount of water in each tank is a constant at equilibrium. In other words, let's say we want to take the ratio of this over this. Two. That ratio is constant at equilibrium at a specific temperature. It doesn't change. Let's say we dump in 75 gallons of water. What's going to happen? We're stressing this equilibrium. We're putting pressure on it. Here it is, nice and nice. Everything's good. 100 gallons, 50. Then all of a sudden I dump a bunch of water and that thing's going to go like this, isn't it? And it's going to reestablish. It's called Le Chatelier's principle. We'll learn it later. You stress a system at equilibrium, it moves to relieve the stress and reestablish. So we put 75 gallons of water in here. This thing will reestablish at 150 and 75. Still equals 2. The ratio stays the same. This is equilibrium. This is what's going on when you ionize weak acids, partial. This is what's going on in any equilibrium. And that ratio is a quantitative number. It's called the equilibrium constant. All right? You won't have a question on the exam. Okay? In fact, this is way more than we would want you to know. But I think that it wasn't difficult, to present it, and I think you have a better understanding now of what equilibrium is. A lot of people, and me included, I remember when I was taking, intro chemistry, general chemistry, I remember, I wanted to say equilibrium, the amounts were equal. That's what it meant. Equilibrium, it's right there, but it's not. Okay, so we're going to memorize our list of strong acids, knowing that the strong acids do not obtain equilibrium. Anything else that's an acid that's not on that list is a weak acid, and they are in equilibrium with their ions. Okay, although the amount of ion production is very, very small. Very small. Okay? Okay. So, we know that acids produce H+. And we know that bases have a couple of different definitions. We're probably going to lean more toward the proton acceptor definition under Bronsted-Lowry. But we're always going to keep back in the back of our mind that if we see OH, we know that according to Arrhenius, that is a base. And that can help us identify our conjugate acid-base pairs. So how do we quantitate the hydrogen ion concentration? How do we put a number on it? Because we can do that. It's called the pH. pH. And incidentally, the lowercase p doesn't mean anything. I've seen some books and heard some people say, oh, it's the power of hydrogen or something like that. It doesn't mean anything. It doesn't stand for anything. In fact, it just tells you that you have to do a mathematical operation. The pH is directly related to the molar concentration of H plus in solution. Okay? And it's a log function. The pH is equal to the negative log of H plus concentration. And by H plus, we actually mean H3O, right? But again, sometimes for convenience, we say H. Right? pH is much better than PH3O. Okay? I hope everybody has their calculators, right? Everybody got their calculators? I want you to locate the log key. It's log. If you don't see it on the key itself, look for the inverse of the 10 to the x key. Look in the blue for the inverse function on 10 to the x, because these are inverse functions of each other. Does everybody see the log? Yeah, big capital letters. Oh, it jumps out of it. Okay? I love these calculations because they're pretty much idiot-proof. Okay? You can't take the log of a negative number. In other words, you can't take the log of -2. It'll give you an error. But you can take the negative log of a number. You just take the log of it, change sign. Okay? So you don't ever have to worry about messing that up. If you try to take the log of a negative number, your calculator is going to say error. Give me a new one. Alright? Something like that. Okay? You'll be given the H plus concentration. All you have to do is do the calculation. Let's try one. Again, these are brackets. These brackets are very common in chemistry, mean molar concentration. They mean molar concentration. That's what those brackets mean. So molarity is what you're looking for. Let's say let's give 2.1 times 10 to the -4 molar. See what the pH is. Now, some of you will have to put the number in first, then hit log. Others will have to hit log first. And the easiest way to figure out which one you are is hit the log key right now. If you see it spells log in your screen, then you push the log key, then put the number in. You could actually hit negative first, if that works. You can actually hit the negative, not minus, the change sign key, which usually looks like this, or this, You can hit the change sign key, then hit log. Gonna get to that. How did you make that come out to 3? Can you set your calculator to show a certain number of significant digits?
Yeah.
Good. Because if you could, I want one of those
I know.
calculators.
No, me too.
Okay, so we're going to put in our formula. pH equals the negative log of H plus. Concentration. I have the concentration. What was that? 3.6 what?
367.
Yeah, give me a couple of them.
Okay, here.
3.6.
6,
6, 7,
7,
7.
8, 0.
Okay, that's good. Everybody get that? Who did not get that?
I actually have an extra 7 in there.
7, 7?
7, 7, 7. 8, 0.
7, 7, 7, 8.
Who gave me that number? Like that? Okay, everybody got that, right? It's really a straightforward calculation, right? These are gimme points. Easy to get points on the exam. So you can't afford to miss it. You can't afford it. So you can make sure and do these calculations correctly. Right? Now, when you're taking the log, significant digits are a little different than what we're used to. How many significant digits in this number? 2. Because it's written in exponential, and we don't even do Atlantic Pacific, right? We just say, it's written in scientific notation, count them all up. 2. When you take logs, when you hit the log key, or for pHs, significant digits don't start until after the decimal. So, 2 significant digits in this number is right there. This answer is 3.68 on the pH. Okay? Logs have 2 parts, a mantissa and an ordinate. And the significant digits are related to one of those. We don't really care. Let's just know that it doesn't start until after the decimal point. So you look at pHs. 10.41, 6.21, 0.51. These all have 2 significant digits. They're all 2 sig figs. Be careful. Be careful when you're doing it. This is only for log. You only have to worry about it when you see pH equals. That's the only time you have to worry about it. Other than that, everything else is the same. Okay? Everybody good? Always remember that. pH is when you gotta have your little red light come on. Now, the pH scale runs (0 to 14). pH scale runs 0 to 14. Right in the middle is 7. Right in the middle is 7. The acids are less than 7 in pH. And the lower the pH, the stronger the acid. So, these are the strongest. These are the weaker. That's kind of the opposite, right? You know, pH of 1 is a stronger acid than a pH of 5. Lower the pH, stronger the acid. The bases run pretty much the same. Bases are up here, greater than 7, with the strongest bases up around 14. Higher the pH, stronger the base. It's the opposite. Here's a weaker acid, weaker bases. Again, 7. There's only one neutral pH, and it's 7. Seven is the only neutral pH. If you're 7.000000000000000 blah 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 1, you are base. If it's 6.99999999999, you get the drift. It's acid. 7 is the only neutral pH. Okay? That close? Maybe. What's the answer?
Base.
It is a base. What's the pH?
7.47.
7.47? Sounds about right. Oh, got the red one. $7.47. 7.47 is over 7. It's in the basic range. This is a base. Okay? Okay. What's the pH? 7. 7.00, right? Notice that this also could have been written like this. Concentration of H plus is 10 to the negative 7. If you see something written like that, most calculators won't allow you to just put in 10 EE, or 1, sorry, you don't want to put that in 10 EE, because that'll actually put it off by a full order of magnitude. You have to make it 1 times 10 to the negative 7. If you put in 10 EE negative 7, it's going to actually make it 1 order of magnitude greater. Okay? That would be times 10 to the negative 6 is what it would ultimately be. Okay. pH is 7 makes this neutral, right? So you can tell kind of qualitatively by looking at the exponent on the base 10 in the scientific notation. Negative 7 is your gray area for neutrality. But if it's less than negative 7, it's base. The last one we did was 10 negative 8, right? Negative 8 is less than negative 7. So if it's less than negative 7, you're looking at a base. If it's greater than negative 7, you're looking at an acid. I promise 100% you're going to have pH calculations on the quiz tomorrow and on the exam coming up for units 3 through 6. What? 4 through 6, sorry. 4 through 6. 4 through 6. You just had 3. Okay. if we write this, look at this equation. This is called the self-ionization of water. Or the autoionization of water, same thing. And this happens anytime you have water. Even aqueous solutions. It doesn't have to be pure water. Anytime you have water, this is going on. Water is ionizing itself. If we go back to our Bronsted-Lowry, we say, we know this is an acid, this is a base. Yeah, pick one. Doesn't matter. The self-ionization of water. Notice in this case, water can act as both an acid and a base. There are some compounds or ions that can do that. They can act as an acid or a base depending on their local environment. These are called amphoteric. I've seen it amphiprotic, amphoteric. Amphoteric, that can act as an acid or base. Autoionization of water is an example of the amphoteric nature of water. The water can act as an acid or a base. This is in equilibrium. And anything that's in equilibrium, it's most things that are in equilibrium, you can calculate an equilibrium constant. And you can do that for this equation. We're not going to go through the math. Okay, we're not going to look at the ratio of product to reactants at this point. But I will tell you that there is an ion product constant. Ion product times, right, multiply times, constant. And for water, we refer to that as Kw. This is the ion product constant. It's only for water. That's why it's Kw. The ion product constant for water means that the concentration of H3O plus times the concentration of OH minus in any solution containing water is equal to a constant. One times 10 to the negative 14. Can you guys see that in the back? Barely? Let me see if this one. That a little better? Okay? What this allows us to do is calculate either one of these given the other one. So if you're given the hydrogen ion concentration for a particular solution, you can calculate the pH. Thank you. Or you can calculate the OH minus. Calculate the OH minus in a solution containing H plus 4.7 times 10 to negative 4 mole. What do we got? That looked about right, yeah. 2.1 times 10 negative 11. That is correct. Right? H3OH plus are the same thing, right? Divide both sides by 4.7 times 10 to the negative 4. Do that math, 2.1 times 10 negative 11. Molar. Is this solution acidic, basic, or neutral? It's acidic. I got one acidic up here. Anybody second?
Yeah.
Guess I
Pretty
can
strong
move that all
acidic,
people.
too.
It's not bad, huh?
It's 3 something.
If the concentration the concentration of H3O is greater than 10 to the negative 7, you will have a concentration of OH minus less than 10 to the negative 7. Because when you multiply them together, you have to get a constant. So if one is 10 to the negative 7 is the break point, right? Because that's neutral. The neutral solution says, can you see back there? You sure? Because there's C right here.
In the way, but
What is? Oh,
camera.
you want to sit up here?
No, it's fine. Thank you.
Neutral solution has the concentration of H3O equal to the concentration of OH minus. The only way you can have H3O equal to OH minus, and when you multiply them you get 10 to the negative 14, is if each one of them is 10 to the negative 7. You can have H3O equal to OH minus, 10 to the negative 3 molar, both of them. But guess what? When you multiply those concentrations together, you do not get the ion product constant for water. So in order to satisfy the two parameters, number one, the concentrations are equal to each other, and when you multiply them together, you get 10 to the negative 14, is if they're both equal to 10 to the negative 7. Everybody see that? Now we did a problem earlier where I asked you to calculate the pH of a solution containing H plus equals 10 to the negative 7. And that pH came out to be 7.00. Some of you may start to see, it's no mistake here that if you take the negative log of 1 times 10 to the negative 14, you get 14. The upper limit on the pH scale. Incidentally, you can't have a number outside 0.14. So if you're on the exam and it says calculate the pH and you get a number 17, you made a mistake. Go back and find it. Your answers can only be between 0 and 14. Okay? So, this is the only absolute situation. If you get H3O plus greater than 10 to the negative 7, acid. If it's 10 to the negative 7, then this is going to definitely be less than 10 to the negative 7. Because when you multiply them together, you got to get 10 to the negative 14. And our base would be the opposite. All you need is one of them, right? Given the concentration of H3O or the concentration of OH minus, you should be able to tell if it's an acid or a base or neutral. We're certainly most familiar with H3O because that gives us pH. But there's an analogous scale called a pOH. It's just a negative log of OH. We won't mess around with it.
So I'm going to ask kind of a silly question probably, but why is it negative 11 and not negative 10?
Was it 10?
No, I'm just asking, how do you get the negative 11?
I get it by dividing this number by that number. Oh, I see, because you're doing negative 14 minus 4 is negative 10, right? Because this number is less than 1. This is 1/4. I can see, let's say that it was 4, okay? That'd be 1/4. Right? So just for the sake of your argument, let's say that it was that. And you want to do the shorthand method. You're going to say when I divide exponents, I subtract them. So negative 14 minus a negative 4 is the same as negative 14 plus 4, which means negative 10. And you're absolutely right, 100%. Here's the problem. What's 1 divided by 4? What's 0.25? Is that a number correctly written in scientific notation? No, it's not. You've got to move this over 1, which causes that to get smaller by 1. So whenever the numbers don't come out to be exactly what they are, like if I'm multiplying, I add. If I'm dividing, I subtract exponents. Whenever it doesn't come out to be that number, that means that your value in front of your scientific notation was a number that's greater than 10 or less than 1. So you got to move the decimal to make it a correct scientific notation. Okay? Everybody good? Okay. You're going to have to do calculations involving kW and also calculations involving pH. Okay? I'm going to give you a little table that's got a little bit more information than what we've covered in here. But I'm going to give it to you anyway because somewhere down the line I think you're going to need it, especially if you take Gen Chem. And it relates pH to PaOH, H plus to OH minus, all of these. Okay, first I'm going to give you the ones that we are using. Okay? I'm going to draw arrows. And what this says is that if you have OH and you want to go to H3O, what you do is divide 1 times 10 to the negative 14 by the concentration of OH. And as you would expect, if you have H3O and you want to go to OH minus, you would divide it. This is kW, right? This is the kW calculations. Whatever one you're given, just divide it into the kW. That's 1 times 10 to the negative 14. Divide it right into it. You're going to get the answer. If you have H3O and you want pH, you take the negative log of the H3O. So when you're looking at using this, you're going to say, what am I given versus what do I want? I'm given H3O, I want pH, negative log. I'm given H3O, I want OH. 1 times 10 to the negative 14 divided by what I was given. So you see how this works. Okay. But there's no cheating. You can't cross. If you're given OH minus, let's say, we haven't done any of these, and you probably won't see it. But if you're given OH minus and you want to know pH, you follow the pathway. You start here, you first go to here by doing that. Once you get here, you go there by doing that. Okay? And really, this is all we're asking you to do, right? Do calculations involving pH using negative log, and calculate one given the other using the ion product constant. We don't ask you to come up with H3O given pH, but you can. So I'm going to put the ones in red that we're not necessarily asking you to do. Better make sure first. Yes. We're just doing KWs and pHs. So pretty much just the stuff in black here. But I'm going to fill in the rest for you in case you ever want to see it or need it down the road, because it's all pretty much straightforward. If we have H3O plus and we want pH, we take the negative log of H3O. If we have OH minus and we want POH, what do you think we do? Negative log of OH, right? Oops. This has got to be in red now, right? I don't want you guys to confuse this stuff. Negative log of OH. See, so that P, whatever it is, means negative log. pH, negative log of H, plus. POH, negative log of OH. pKa, negative log of Ka. Means take the negative log. Here are some ones that you might not have known. If you have POH and you want to get to OH, you simply raise power 10 to the negative POH. So if your POH is 3, and you want to know what your OH is, it's 10 to the negative 3. You just raise 10 to the negative power of the POH. Same thing over here with pH. Again, you're not going to have to do these. If you have pH and you want to know what H plus concentration is, you find your 10 to the x key on your calculator, you put in the negative pH, and you hit 10 to the x, and it gives you the answer. Lastly, we know that the pH scale ranges from 0 to 14. So if you have pH and you want POH, it's just 14 minus the pH. 14 minus the POH. And you have yourself a little table that relates all 4 of the values. Again, all we're going to want you to do is run with KWs and calculating pHs. Remember, when you calculate pH, when you hit that log key, remember significant digits don't start till after the decimal. Okay? This is all you need to know, these 3 arrows. For now. But any of you go on to university and take another chemistry, maybe send me an email saying, oh, thanks. Okay? Questions? Everybody good with those calcs? Because you're going to have a quiz tomorrow, right? You're going to prove it to me tomorrow. We'll take the quiz before we start the lecture. Okay, and we can get it out of the way. Good? All right. Okay. Only got a couple more things. You can react acids with bases. This is a neutralization reaction. An acid plus a base always produces a salt plus water. Always. This is a general reaction type. Acid plus base, salt plus water. This is nothing more than a double replacement, right? Look at it. I'm going to put Na with Cl, and I'm going to put H with OH. That's H2O. So this is aquated, this is liquid. This is a subclass of double replacement. Which means all acid-base reactions would be double replacement. But not all double replacements are acid bases. We've seen some double replacements. Pretty much all of Lab 4 that you're going to hand in today, it's all double replacements. It's called a neutralization reaction. It's a neutralization reaction. You can write balanced molecular equations, balanced formula equations, right? Ionic equations and net ionic equations for these. Let's pick a different one. I don't want to use NaCl if I don't have to. Yeah, here's one. Let's do nitric acid. We'll do naming in just a minute. Plus sodium hydroxide. Nitric acid plus sodium hydroxide goes to sodium nitrate and water. Is it balanced? Looks balanced to me. One sodium, one nitrate, one nitrate. We really should be saying one nitrogen, 3 oxygens, one oxygen, 2 hydrogens. We're balanced. Right, total of 4 oxygens. 3, 1 is 4. Do you recognize this as a salt? Probably not, right? Probably not. The most familiar salt to you is NaCl, right? So when I did this one up here, you're probably like, oh yeah, of course, that's a salt is the anion of an acid. What's the anion of an acid? That's going to be anything except the hydrogens that are written out front. That's the anion of an acid. So, is NO3 the anion of an acid? Yeah, of course it is. It's right there. That's on your list of strong acids. You'll get familiar with those anions once you start memorizing the list of strong acids and as you get exposed to other weak acids. Okay? the anion of an acid combined with a cation other than hydrogen. Of course it's other than hydrogen. If it was combined with hydrogen, it would be the acid. Right? As you become familiar with your acids, these anions will become more and more familiar to you. I just told you that nitrate is the anion of an acid, specifically this acid right here. So anytime you see nitrate with something other than hydrogen, it's a salt. It's a salt. Most ionic compounds, I want to say all ionic compounds, but I hesitate to use that word. Most ionic compounds are salts. They are anions of acids, a whole bunch of acids, combined with something other than hydrogen. Look at NaCl. The anion is Cl minus. That is the conjugate base of HCl. Remember that conjugate acid base? So, I don't want you to get stuck into thinking that NaCl is the only salt. No, there are hundreds and hundreds and hundreds of salts. And most of them are soluble except for those specified in our solubility rules. Right? So, here's our balanced formula equation. Now we want to write our total ionic equation. HNO3, does that break apart? Why? Why? What is? You want to say solubility rules, all nitrates are soluble? Here's the problem. Those apply to ionic compounds. This isn't an ionic compound. What is this?
Covalent. Polyatomic.
It is polyatomic, but what is HNO3? What's the name of this unit?
Molecule.
Acid. It's an acid, right? It's a strong acid because it's on our list of strong acids. What do strong acids do? Break apart virtually 100% of the time. So our solubility rules are going to get kind of freaky on us here. The solubility rules only apply to ionic compounds. These we're now talking about strong acids and strong bases, weak acids and weak bases. Strong acids, strong bases break apart 100% of the time. Weak acids and weak bases don't. HNO3 is a strong acid. The only way I know that is because I memorized it from the list of strong acids. And that's the only way you'll know it as well. So it does break apart. NaOH. Does that break apart?
Oh, yes.
And all I had to do is look at you and change your mind.
Yes.
NaOH is a strong base. How do you know that? I'm not going to make you memorize the list of strong bases. But if you look at your periodic table, you can get a real good idea of strong bases because they're the hydroxide forms of these six. Start at lithium, go down to potassium, over to calcium, down to barium. That's a good start. Otherwise, there's a list of them. You showed me it earlier. Yeah, strong bases. We have sodium hydroxide, potassium hydroxide, and calcium hydroxide. I guess that's all we care that you know. So, sodium, potassium, and calcium. So, let's just go these three. They're right near each other on the periodic table. Group number 1. I can't see. I know you can't see. Okay, so sodium hydroxide does break apart. because it is a strong base. Okay? An argument could be made, using the solubility rules. I think something in solubility rules said all hydroxides are insoluble except sodium, they had some exceptions. Sodium nitrate, yep. This one now does apply to solubility rules. It's a nitrate and sodium. So we're going to break that apart. What about H2O? Does that break apart? Have we ever seen water as an acid? Yeah, we did, right? It can be a base too. Is it on our list of strong acids? No. And therefore it is a weak acid. Right? And what do we say about weak acids? They don't break apart. Keep it together. Keep it together. All acid-base reactions, the driving force is the formation of water. Net ionic. Cancel, 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 cancel. We're left with there's our driving force. Notice you can't see that. You wouldn't be able to see the formation of water on the desk. Right? You wouldn't be able to see that. Sorry. But it's there. Any acid-base reaction, salt plus water. These aren't handled any differently than the ones that we saw previously with balanced molecular, total ionic, and net ionic. Okay. All right. Let's name these things. Let's name our acids. Acid nomenclature. First of all, all acids start with H. All acids begin with hydrogen. Unfortunately, not everything that begins with hydrogen is an acid. That's the unfortunate part. There are compounds that start with H that are not acids. Unfortunately. But for us, in naming, all of our acids will start with H. First thing we want to do, identify the anion of the acid. We want to identify the anion. What is the anion? We just said that a minute ago, right? This is everything except the hydrogens written out front or written first. We just said that all acids start with hydrogen. In order to identify the anion, all you have to do is cover up the hydrogens that are written out front. Acid, anion. Here are some examples, or here's a list of acids. What are the anions? Everybody got those written down? In order to determine what the anions are, all you gotta do is cover up with the H's that are written up front. So the anion Cl minus, SO4 2 minus. Oh, I put H3PO4 twice, right? You need to identify the anion. Now, there's going to be two main classes. The first, the anion does not contain oxygen. And then the second one we're going to do is the anion does contain oxygen. So, if the anion contains oxygen. No, it does not, right? Sorry. We're going to do does not first. The anion does not contain oxygen. If the anion does not contain oxygen, you are going to name the acid hydrorootic acid. Example, HBr. Anion, no oxygens, hydrobromic acid. If it doesn't have oxygen in it, you will start it with the prefix hydro. HCN. What is it? What's CN minus? Cyanide, right? So it's got to be hydros something, right? Hydrocyanic acid. Notice it's cyanide, bromide. So, I mean, you could make an argument that you change the IDE to IC. This was bromide, becomes bromic, hydrobromic. Okay, but the roots are going, they're going to be pretty much the same as they were when we were doing inorganic nomenclature, binary compounds. Chloride bromide. Okay. Now, what happens if it does contain oxygen? If the anion does contain oxygen, the first thing you have to do is name the anion. If the anion contains oxygen, you more than likely have a polyatomic ion. And whether you've noticed it or not, most of your polyatomic ions end in ATE or ITE. Nitrate, nitrite. Phosphate, phosphite. Oxalate, I don't know if oxalate's on. Okay? Name the anion. If the anion ends with ATE, drop the ATE and add IC plus the word acid. HNO3. NO3. Nitrate. Nitric acid. HC2H3O2. What is the anion? C2H3O2 minus. What is that? Acetate. Acetic acid. In its highly purified form, glacial acetic acid. This is vinegar. We eat it. Name the anion. If the anion ends in ATE, drop ATE and add IC plus the word acid. There are two exceptions where the strict application of this doesn't give you the name of the acid. Except H2SO4. SO4 is sulfate. ATE drop. IC sulfic. No. This is sulfuric acid. The other is H3PO4, which becomes phosphoric acid, not phosphic. Everything else pretty good. Everything else falls in line pretty darn good with our rules. Okay? If the anion ends with ITE, drop the ITE and add OUS plus the word acid. So eights become icks, ites become us. Eights become ick, ites become us. HNO2, anion, NO2 minus, nitrite, nitrous acid. We have the same exceptions. H2SO3 becomes sulfurous. H3PO3 becomes phosphorus. Okay? You already memorized your polyatomic ions, so this is just extra credit, right? This is just another exam where you get to get more points because you memorize those polyatomics, right? Anything that all acids start with H, once you have an acid, remember this is only for acid naming, okay? It's not for anything that starts with an H. So, identify the anion. If the anion does not contain oxygen, hydroruic acid. If the anion does contain oxygen, you name the anion. H become ick, ites become us. This is acid naming. Notice, you will never have hydro on an acid that has oxygen in it. Right? Hydro is reserved only for anions with no oxygen. Try one. Try a couple. Let's see if it remembers. Do you have your list? Oh, yeah. I don't want to give you any anions there. What is that?
Carbonic acid.
Carbonic acid. CO3 2 minus is carbonate. How'd you know that? Memorized it. Carbonic acid. Chloric. Yes. Very good. ClO3 minus is chlorate. Chloric acid. Notice HCl. What's HCl? What's HCl? Hydrochloric. Notice how close they are. Chloric acid versus hydrochloric acid. Only a name. Formulas, no. Not at all. Okay, so you will see those. The acid-base titration section we're going to cover in lab. We're actually going to perform the lab and do the calculations. So there's nothing in the book except the description. So read that over and just be ready for lab. We'll dissect that pretty good when we do a practical application of the titration. Last thing is buffer. Buffer solutions. Does anybody know what a buffer is? Buffer. Buffers are solutions that resist changes in pH. With small additions. Buffers are solutions that don't change their pH when you add a little bit of acid or a little bit of base. You can overload a buffer. Easy. You can add so much acid that it overloads a buffer and you start to see the pH plummet because it's acidic. The best buffers are weak acids and their conjugate bases. Best buffers are made up of weak acids and their conjugate base, i.e., acetic acid, acetate. if your buffer resists changes when you add small amounts of acid or base, doesn't it make sense that they have to have some way to neutralize that added acid and added base? Otherwise, that added acid or added base would affect the pH and cause it to change. So, something in the buffer has to be able to deal with those added acid or base. And this is what it is. Okay? If H3O plus is added, what do you think neutralizes the added H3O plus between this and this? What is H3O plus? What is it? H plus, yeah, same thing, right? What is it though? What's the name of this unit? It's an acid, right? Remember? You don't see it all the time, but when you do, it's always an acid. So, which one of these components is going to neutralize that?
The base, which is on the right.
The base.
Except the H plus.
The base will. And this is a base. Remember, these are conjugate acid-base pairs. They only differ by one hydrogen. This is the acid. This is the base. So, if I add acid, it's neutralized by the basic component. Alternatively, we could show that as H3O plus C2H3O2 minus would go to HC2H3O2 plus water. Same thing, just that shortcut way you take the water out. If OH minus is added, what component neutralizes the added OH minus? The acid, right? The acid, because OH is a base. So here we would have the acid component reacting with the added base. Now, this is a weak acid because it's not on a list of strong acids, which means it only partially ionizes. It only partially gives up its H plus. Okay? It doesn't want to give up its H plus because it is a weak acid. But faced with a strong base, that strong base will go in there and rip that thing right off, and it won't have anything to say about it. It won't give it up normally or voluntarily, but with a base in solution, it sure the heck comes off of it. All right? So this comes off, and we get the OH grabs the proton and forms the acetate. we see how a buffer works. A buffer has both an acidic and basic component, a weak acid and its conjugate base. If you have a weak acid, we know that weak acids don't want to break apart. They only break apart partially. They partially ionize, right? So the H plus, the proton, and the anion are happy together. They don't want to break up. So the base, the conjugate base, is very strong. Because if you put an H plus in and around this acetate, it's going to grab it real quick and become that, which is very happy. So weak acids don't want to give up protons. Have very strong conjugate bases, because the base is going to want to grab those protons and form this thing back. All right? Weak acids have strong conjugate bases. It's always the opposite. Strong acids have weak bases. Strong bases have weak conjugate acids. It's always the opposite. Right? These two components, the weak acid and the conjugate base, are capable of dealing with any added acid or base in the buffer solution, and they neutralize it before it has an opportunity to affect the hydrogen ion concentration, the pH. If you add acid, the base goes into action. If you add base, the acid goes into action. But notice what's produced in each reaction. If we add acid, what's produced? Acid. Right? If we add base, what's produced? Base. This is interesting, because this is how the questions are going to be asked. We're going to want to know, how will a buffer respond to added acid or base? And I'm going to show you the real easy way to get those answers. We just said that if you add acid, the buffer responds by producing its acid. If you add base, the buffer responds by producing its base. So once you know what your buffer looks like, don't read into these problems, okay? Don't read into them. Don't make them more difficult. First of all, you're going to know what your buffer is. You're going to know the acid and the conjugate base. It's going to be given to you. So you label it. These are conjugate acid-base pairs. Which one's the acid? Yeah, this is the acid, this is the base. Right? What are we adding? Base. The buffer responds by producing base. That's it. That's it. Whatever you're adding, acid or base, in this case we're adding base, go to your conjugate acid-base pairs and identify your base. The buffer responds by producing more of that. That makes sense. Because the OH is going to be neutralized by this, which is going to rip that hydrogen off and make that CO2 minus. Does everybody understand that? And the answer will be by producing more. Okay, those would be the answers. And it doesn't matter what it looks like. How will this buffer respond to added H+?
Whereas
Which is?
the H2 phosphate,
That's right.
or the dihydrogen.
Dihydrogen phosphate. Notice you wouldn't use acid naming on this, right? Because it's not an acid. Acids are neutral. Our naming was only for neutral acids. This is a polyatomic ion, which you memorize. If it's neutral, we can use the procedure we just developed for naming acids. If it's not neutral and it's got a charge on it, it's got to be one of your polyatomic ions that you memorize. This buffer would respond by producing okay. Can we do one more? Do one. That's actually a strong acid, right? I don't want to use a strong acid because that's not right. Sorry, you guys. I'm getting tired. Yeah, let's, how respond to added OH. How will it respond? More base, which is which one? This is a base. Here's our acid. There's our base. This is a base. Okay. Everybody good? Question?